So as we start this video, let's take stock of where we are. We started with this Segway problem with this wheeled vehicle on a slope, has to balance itself. We derived some nonlinear, fully nonlinear differential equations which model the system using Newton's laws of motion. And then what we did, in order to analyze it more thoroughly, we linearized the equations. We found an equilibrium. We found equilibrium conditions. And then we linearize these nonlinear differential equations about that equilibrium condition to obtain these equations right here. And although we have obtained linear differential equations, we are not quite done yet, because what we want to do is represent these equations in this standard form for linear control systems. That is, we want to write the equations as a system of first-order differential equations. That looks like x dot is equal to a times x plus b times u. In this case, the state of our system, x, we'll write as theta, actually theta tilde dot, phi, and phi dot. So notice that there are four states. Therefore, the A matrix is going to be a 4 by 4 matrix, right? Therefore, the A matrix is going to be 4 by 4. I'll fill in some of the details soon. How about U? What is U? I don't see a U anywhere in my linear equations. Do you? There's no U. But let's think about what U is. U, recall, is the control, right? It's the effect of the control input. It's the things we use to push or pull on our system. And for the Segway, the thing we use to push or pull on the system is the motor torque, the tau. And after we do the linearization, what survives of the motor torque really is this tau hat we see in two different places. So it's the tau hat. That is the U. Right there and right here. There's our U. I call it tau hat in these four equations that I've written so far, but from now on I'm going to call that U. That's our control input. This is the amount of motor torque we have to put above and beyond the equilibrium motor torque to keep our system, hopefully stabilize our system, to give it dynamics that we desire. And notice in our system, we only have one control, this motor torque. We have nothing else, right? It's not like your project that you're doing for the class where you have two inputs. This is just one. And therefore, you can determine that the B matrix has to be n by 1. So actually, let me put the x and the a and the b and the u all together in one piece so we can see how it fits. Putting all the pieces together, this is how our linearized system of equations are supposed to look. Before we start filling in some of the blanks, notice that there is no constant term, right? All this stuff here depends upon the state. All this stuff over here on the right side, it depends upon the control. There is no plus c on here, right? So you remember when we were deriving the linearizations, there were all these constants floating around, and we were able to cancel out all the constants. Because we were able to cancel out all the constants, we don't have a constant term floating around. And that's very important because the control theory for linear systems is based upon a form of equations that look like this, no constant term. As a result, when we say theta tilde, for example, we're not talking about the actual lean angle for the Segway. We're talking about the theta tilde represents how much the Segway is leaning relative to the equilibrium lean angle, right? And likewise, the U is the amount of motor torque on top of the motor torque necessary to hold the equilibrium. And we can go a little farther here. So let's take this first equation. This first equation says the time derivative of theta tilde is equal to, what's that going to be? That's what my first row tells me. Well, this is one of these definitional equations that allows us to put it in as a system of first order equations rather than second order equations. So the time derivative of theta tilde is going to be theta tilde dot, by definition. So therefore, what I'm going to have is a 0 here, a 1 here, 0 here and a 0 there, right? So theta dot is equal to theta dot. Again, by definition. And the u does not appear in that definition at all. So I'm going to put a 0 there as well. And I can do the same thing on the third row. That is phi dot, time derivative of phi, is going to equal 0 times theta tilde plus 0 times theta tilde dot plus 0 times phi plus phi dot, right? So phi dot is equal to phi dot, and no u's coming into there. So there's that. And then what do we have for the rest of these equations? Now we're going to start looking up to what we have, what we derived previously. But notice this right here. It says the time derivative of theta tilde dot. That's our second equation here. So this is theta tilde double dot, right? And that's going to have some stuff in there. And then on the fourth equation, the fourth row here, we're going to have derivative of phi dot. So this is going to be phi double dot. So I got theta tilde double dot, phi tilde double dot. And if we look above into those linearized equations that we derived last time, here's how theta tilde double dot, here we see it again and again, and phi double dot, again we see phi double dot 4 places. This is how they're related to each other. And notice I have here 4 equations, 4 linear equations for 4 unknowns. My unknowns are the theta tilde double dot, the phi double dot, the hx tilde, and the hy tilde. So I've got 4 equations with those 4 unknowns. In particular, what I'm going to have to do is I'm going to have to solve them for the theta tilde double dot and the phi double dot. I'm going to have to do that solving in order to fill in rows 2 and rows 4 in my linear equations. That includes the u here. But before we solve it, we can actually see some more structure to this equation if we look hard enough. So what I want you to do, let's go back up to these things. And let me ask you a question. Do you see a theta tilde dot anywhere? Look at equation number 1, no theta tilde dot there, or here, or the third one, or the fourth one. There is no theta tilde dot. So therefore, theta tilde double dot and phi double dot will not depend upon that theta tilde dot. And for that reason, I should be able to put a 0 right here and right there. Right? There's no theta tilde dependence. Ooh. Well, is there phi dependence or phi dot dependence? Let's go back up and look. If you look at these 4 equations, you will not see a phi or a phi dot. So therefore, we expect more zeros. 0 right here, right here, right here, and right there. Wow. I've gotten most of the structure of the equations without doing anything, really. Actually, I did a whole bunch of stuff, but I'm not using that stuff yet. Okay, but there is going to be the theta tilde dependence, right? The theta tilde is right here. There it is. So we will have that dependence. And there is a u dependence, right? Here's the control input. So we will have something in these other boxes that I have not filled in yet. And let me just call this A21. I'll call this A41. So we expect there to be an A21 and an A41. We also expect there to be, I'll call this a B2 and a B4. To determine those coefficients in the A and B matrices, we're going to have to rewrite our linear equations 1L through 4L. And we can do it like this. That is, I can take my unknowns and I can arrange those terms in a form that I can express as a matrix. And I can look up the elements of Q term by term directly from, because for example, in equation 1L, theta double dot is multiplied by a minus d cosine theta equilibrium. So minus d times theta times cosine of theta equilibrium is going to be in this upper left-hand corner. Again, I can read off the rest of the coefficients just from the equations. So that all goes on the left-hand side of my equality here. On the right-hand side are the theta and the u dependents. So I'd look up all the terms with the theta in there, and as I recall, there was just one of them. And that's going to go in the third element of this thing I'm calling r theta. The rest of those elements are going to be 0. And then what I'm going to do is I'm going to look at where u appears in the equations, and that's going to appear in the third and the fourth equation. So the first two elements will have zeros, and the third and the fourth elements of RU here are going to have coefficients in there. The important thing is that I'm going to be able to invert this 4x4 matrix Q. At least I hope I'm going to be able to do it. And if I can solve for these unknowns. And the solution is going to look like this. So this matrix right here, multiplying the theta tilde, that's going to be Q inverse times R theta. There's R theta right above. The matrix multiplying U here is going to be Q inverse times RU. Again, this assumes that we can invert that Q. And when we do it, guess what? The element right here, that's going to be the A21 that we were looking for. And the element right below it, that's going to be the A41. This is the A21 and the A41 that goes into the A matrix of our system of linear equations. Furthermore, the B2 and the B4, guess what? They are right here and right here. We'll get some other stuff in these two elements, but the ones in the first two rows are what we're after. This process is going to give us our system of linear algebraic equations with the control in there. You may recall in a previous video we had started this MATLAB live script called Segway analysis. This is where we define parameters, we solve for the equilibrium motor torque and the equilibrium lean angle, and we're going to continue this document to determine the system of linear equations. All right, so now the part we're going to add is the linearization. So here I describe the linearization similar to how I do previously in the video, and I don't need to go over that again. I've got some common terms that occur in my equations, so I just define new variables, then write out the cosine or the sine of one of these angles multiple times over. So here I construct the Q matrix, the R theta matrix, and the RU matrix, and I can run those so that they're now in memory. And let's see. Before I go on, remember I questioned whether Q, or at least I had the question in my mind, whether Q was invertible. So let's go ahead and test that. And the way we check that this thing is solvable or invertible is we take the determinant of Q, and if it's non-zero, then we're in good shape. So let's just check it real quick. So 0.02, it's not far from 0, but it is non-zero, so we should be able to invert here. And we actually might want to do a condition number 2 just to check it out. So if I say cond, that checks the condition number of Q. Just because we've got a determinant close to 0, we're going to check this out. And the condition number is 32, so that's not too bad. Could be a lot worse. Could be in the thousands. Okay, so we're going to go ahead and invert. So right here, I calculate the Q inverse times R theta, Q inverse times RU. So I have them available. So after multiplying these two matrices out, now it's time to construct the canonical linear control system, x dot equals ax plus bu, where the a is this matrix right here with these special coefficients that we just calculated, and the b is right there. And let's go ahead and fill those out. At this stage, constructing the a and b matrices is really a matter of following the recipe that was outlined before. So I'll just put it in here like so, and then give you the results. Of course, it's good to look at the results the first time you enter them. But as far as the analysis goes for the project, as soon as you got these results, you don't need to look at them anymore because we'll just use the matrices later. So I'm going to put these semicolons here to suppress the output. And now we have the matrices A and B for our canonical linear system. And just out of curiosity, I feel like calculating the eigenvalues of A, right? Those are the dynamics of the system without any control. So I type eig A. So this will calculate the eigenvalues. And before I run this, I want you to think what the eigenvalues should be. What are your thoughts? What are your ideas? Should all the eigenvalues be negative? Should I have complex eigenvalues? Some real values, some positive ones, some negative ones? I don't know. What do you think? Again, pause, because I'm going to hit the enter key in just a second. All right, here goes. The eigenvalues are these. I got 2 zeros. I got a positive value. And I got a negative value. All four are real. So I'm going to let that sink in a bit and see if that makes sense to you. All right, we're done with the video for now.